Welcome everyone to this, our third and final event in this series on high throughput computing with Dask. I'm David Swenson. I'm going to tell you a little bit about what we'll be doing today. We'll be talking about Dask Job Queue before I get around to introducing our presenters today. So the first thing we want to do is show you how to get the tutorial launched, because this may take a little bit of time if you haven't already installed everything. Then I will talk a little bit to fill in the time while it's installing. One thing you'll need to do is to stop any existing processes that are using Dask. This would be anything in a Jupyter notebook, especially that might have been using Dask before. The reason is that if you don't do that, that'll interfere with the way that we communicate with the dashboard to see what's happening inside a Dask cluster when we use our Docker container. The rest of this is only relevant if you're with us last week. We've updated our Docker container, and so we want you to get the newest version of it. And if not, always the up-to-date install instructions are at the link at the bottom of the page. So if you were with us last week, make sure you've updated your copy of Job Queue features. So that's either downloading the latest version or just doing git pull if you cloned it. Then change into that Job Queue features tutorial directory and then run these commands. You're first going to run source jupyter.sh, so that will define the rest of the commands. Stop slurm will halt any existing Docker containers from our slurm cluster. This is if you have left your computer running since last week, like I usually do, you'll want to make sure that you don't have any of these things currently running. Clean slurm will uninstall all of those containers. And then start tutorial will do the whole installation procedure with all of that. Now I'll talk a little bit about the organizations that are supporting us here. CCAM is the Centre Européen de Calcul Atomique et Moléculaire, the European Center for Atomic and Molecular Calculation. It's an organization with over 50 years of experience around organizing events and like workshops, schools, and conferences for computational and theoretical chemists to help us share information and to build community. What CCAM has specifically been doing for this series of events is providing a lot of logistical support, both in terms of helping people be registered and things like that, but also in terms of helping us with the streaming process. ECAM is a European Union Horizon 2020 Center of Excellence with a lot of organizational overlap with CCAM, as well as support from Praise Sites, the Center for Industrial Computing, and our industrial partners. So ECAM is about bringing theoretical and computational chemistry towards the exascale. And that's a lot of what we're going to talk about today. The stuff that we really want to do today will be talking about how you can push further to the exascale using Dask and tools that by wrapping tasks in Dask. So the question today is, what if your task can be parallelized? We've talked about this idea of task-based computing, where you describe your program as a set of tasks. The output of one is the input of the next one. But what if the individual task can be parallelized? For example, in my own work, I work with molecular dynamics trajectories. These are already highly parallelized. Maybe task A and task B in this picture are molecular dynamics trajectories, and maybe I don't know how long they'll even run for. Then task C needs input from both of those. How can I efficiently use the computational resources that I have? Well, task-based computing, tools like Dask are really good at that. We saw last week with Dask Job Queue, how we could scale up and scale down our cluster as it was needed. And so that's exactly what we want to be able to do here. And Job Queue features will now enable us to do that if our task is already parallelized inside itself. A little bit about a few different parallelization paradigms. I think that those of you who know much about parallelization are quite familiar with this. Most of people in scientific computing have at least heard of OpenMP and MPI. But OpenMP, the idea there is that it is only if you have a shared memory space. So that's usually within one node, but it also has the least overhead. MPI has a little bit more overhead, but it allows you to scale out to many, many nodes all at the same time. And it's very common to use these two things together. That our software and scientific software is often loops that have inner loops that then have even further inner loops. And on one of those inner loops, you'll often use OpenMP to parallelize it. And then what you do is on an outer loop, you use MPI. So what we're suggesting, what we think will really help tools like Dask help us reach the exascale, is to add yet another layer, a third layer outside of that. That would be these task-based frameworks. They have more overhead, but they also have more flexibility. And that, again, is what JobQ Features is all about. So in the context of this whole series, in January, we talked about Dask, the core library. We talked about how it sort of integrates with Pandas, with scikit-learn, with NumPy. We talked about how you can achieve parallelization within one node, and we talked about how it lets you do things that you couldn't even fit into memory otherwise. Last week, we talked about Dask JobQ, and with Dask JobQ, we showed how you can take Dask, the same things you wrote with regular Dask, and suddenly now you can use it on your HPC queuing systems. And that makes it so that you can really scale up to very large calculations. And today we're going to talk about JobQ Features, which adds more complicated workflows, such as having MPI within your tasks. So at this point, hopefully you're getting close to having your things set up and running. The way that you will know whether it worked, whether you had any problems, is to look at the end. You'll launch your browser at that link that it says, and you should check that these port numbers are here. So the exact number that you'll have for the one that launches the Jupyter notebook, that may be totally different, probably will be totally different from what I have. However, the Dask dashboard should be 8787. I think that if you have a problem, you'll just see nothing there for either of those. If you don't see the one for the Dask dashboard, that means you have something else using port 8787 somewhere on your system. So that probably means you have Dask running somewhere that you need to shut it down. If you don't see the one for opening your browser, that probably means that you didn't stop a previous session, and you need to do a stop slurm before running it. So hopefully everyone's getting there relatively soon. Now I will introduce our presenters today. So presenting will be Alan O'Cash, who's a research fellow at Jülich, and then helping with questions will be Adam Włodarczyk, who is a software engineer at the Wrocław Center for Networking and Supercomputing. We've had great speakers all the way through this, people who have been really expert on the topics they're talking about. There could not be better people to cover it today than these two people, because they've pretty much written most of the code. So with that, I will pass the floor to Alan.
Great, thanks a lot, David. Let me just get my screen up here. Okay, so I actually wanted to start off just by giving a couple of slides to give some context for where we came from. I think Dave has done a pretty good job of introducing the basic idea. I wanted to talk about why this is interesting for me, for somebody who works at Jülich Supercomputing Center, and I think the context of Jülich Supercomputing Center maybe has something that will help explain that. So yeah, the library we've written is called JobQ Features, and one of the main idea behind it is that we want to reach extreme scale through high throughput computing, right? So high throughput computing is a lot I see with the communities that I deal with in the Center of Excellence that I work in. So why do I want to talk about extreme scale? Well, it's part of a wider European context, okay? So there's something called Euro HPC, which is a multi-billion euro effort, right? Funding effort in the European Union. That's focused on HPC and very, very large scale machines. So it's good. It's a huge amount of funding. It's something like it's in the tens of billions over the next 10 years. So I mean, ultimately, it's going to be a computational laboratory of unprecedented scale in the European Union and available to European Union scientists, right? But you know, even if it's a very big resource, it's still going to be competitive. There's still going to be a lot of people who want to use it, and so that's going to be competitively allocated. And when you want to use these kinds of resources, you need to be able to prove that you can actually use them efficiently. Also, you have to be aware that these kinds of architectures are likely to be pretty new, perhaps pretty unusual. Sometimes that makes them hard to use. It can also mean that using them might be a little bit immature, and the software that's there to support you in using them might not be as mature as you might expect, say, as x86 chips or something like that. But at the same time, you have to keep in mind that they're very big and they're going to be free to use as well. So these are like important points to take note of. So who I spend most of my time working with is the ECAM, which is an HPC Center of Excellence. That's one of about 12 in the EU right now. Actually, maybe one or two more than that right now. The idea, or what I'm trying to do, is to help support the community to adapt to this kind of environment, right? So whether it already exists or it's coming, and to make sure that the community is ready for this change and ready to take advantage of this resource. And what I've seen in the community that I deal with is that there's a pretty heavy use of community codes. There's quite a few people who add value on top of community codes. So they take community codes and then they do something else on top, right? So they use the infrastructure that comes from somewhere else and then add a little something extra on top. What I've also seen is that pretty frequently there's a need for ensemble calculations in the community. So people do pretty large sampling of using computational tools. So that's also something that I see. So, and that's something that maps really well to the high throughput frameworks. What maybe is a little bit interesting to quickly look at is the hardware plan in Jülich Supercomputing Center. So in the past, or like back in 2012, the center was pretty good at keeping two different streams. They had a highly scalable system, which the last one of which was uQueen, and then they had a more general purpose cluster, right, which was just a cluster system, but there was a lot of people who were well suited to that environment. uQueen was a little bit harder to use, but it was much larger in scale. And after that, then in recent times, Jülich has moved towards this idea of modular supercomputing. What that means is that you have a single machine that's made up of different parts, right, different capabilities. So what we've seen in the most recent machine, the first in that line that got turned off this year was Eureka. So we had a Eureka, which was a cluster system that was coupled together with a booster system, which was made of Knight's Landing, so a kind of a booster chip that came from Intel. And now in the most recent system at Jülich is also this kind of cluster booster technology, but with scope to expand into more modules, right? So the cluster system that we had that was in 2018, that's a 12 petaflop system. And the booster that just came online in the last 6 months, that's a 70 petaflop system. And those two are coupled together. You can use them both at the same time. And that's a pretty interesting system because that Joules booster on its own is already the largest system in Europe right now. So in terms of the architecture of those systems, it's also interesting to see that they are also diverse, right? So even the CPU architecture on the cluster and the CPU architecture on the booster are different, but they can still be used together at the same time. In terms of the GPUs on the cluster and the booster has the latest NVIDIA GPUs. The cluster has ones that are one generation behind. And then we have another system, another Eureka system, which still has the booster, the Eureka booster, but we've updated the cluster partition there so that's AMD chips together with NVIDIA. So it looks a little bit like the Joules booster as well. And then we have a number of other systems that also use this kind of technology. So that's kind of the part of the motivation. And then maybe a question that somebody is pretty reasonable to ask is, why did we bother developing our own library, right? Isn't there other solutions out there that already cover this case? And there are lots of like solutions out there, potential solutions, and we looked at quite a few of them. So we looked at PyComps, which is something that comes out of Barcelona, Barcelona Supercomputing Center. We looked at Celery as well, and Dask, and a couple of others at the time as well. But there were really none that we could see, at least, and maybe things have changed since we looked, that completely addressed our expected use case. So we didn't really find something that was able to deal with MPI and OpenMP workloads, multi-node workloads, the potentially heterogeneous architecture that you find like we find now in Joules, and also the ability to fork out MPI tasks to the MPI launcher, or to actually launch MPI aware tasks themselves, right? So those are two different things, and we'll look at them a little bit closer in a while. And we also want to avoid the resource manager as much as possible. So kind of we see an expense in having to go through the resource manager. So when I say resource manager, I mean PBS or Slurm, and we want to do something yet. We want to avoid using that as much as possible, right? So kind of we want to create our own scheduler within a scheduler, or at least that's what we were looking at. For us, Dask came pretty close to what we needed, and it was heavily used. And it was relatively easy to extend because there was already quite a few projects like Dask Job Queue that were already built upon it. It was a Python framework, so that made it, for us at least, because we have experience there, a little bit easier to program. It also, because it was in Python, it gave us this ability to leverage MPI for Py as well. The infrastructure itself was pretty mature. I mean, it was pretty heavily used at that time. And of course, the big plus is that we can take all of that infrastructure. So the task management responsibilities, we were able to leverage all the things that already exist in Dask, and just focus on the extensions that we needed to make everything work. And how did we get to where we are now? Well, there was a collaborative project with Praise. We've had two of those now, so that's with the guys that David mentioned from Poland, so Adam and Mariusz and Miłosz as well. We had something that's called, we have these workshops every so often in our project, which are called extended software development workshops. So where we spend like a week working on code. We had one of those last year in Turin. That was like, we had it basically on Dask in general, and also on the initial implementation that we had of job queue features. Actually, it wasn't last year, it was 2 years ago now. And last year is the duck. And we had two white papers on this in 2019 and 2020, and then since 2019 we've had more or less full support for MPI aware task. We've been tuning that since then. In terms of what are our restrictions right now on the tasks, well, because we're working in Python, we need to move information around these. The tasks need to be serializable, and the return values need to be serializable as well. And we only have access to the memory space of the root of an MPI task. So if something if a task is launched in MPI space, we can only see the memory space of the root task. So we can't see it. We can't directly see it for the other tasks within MPI. The other thing is that the tasks that we give, they have to be well behaved. So what do I mean by well behaved? I just mean that they shouldn't like pollute the memory space. So, you know, try to avoid memory leaks or leaving things lying around the memory and not cleaning up after yourself. And an MPI task, they should not call MPI finalized. The reason that they shouldn't do that is because we reuse the MPI environment. Okay, so when you call MPI finalize, you're actually effectively going to kill our workers. Which is fine, we can recover from that, but it's expensive because it means submitting a new job. And to be honest, we don't really know where the problems are. I'm sure there are plenty there, but we would need more users to be able to see what they are. So with that, I'd like to actually get started with the tutorial itself. So hopefully you've got the tutorial launched and you see a picture similar to what I see right now. And so we have 5 notebooks that we're going to go through right now, and then on the right, then we have the Dask panels as well. So we're able to see some information there as we look. Let's get started with the first notebook. So this is on Decorators. We use Decorators to hide things away. Okay, so we use Decorators because we have some complex things and interactions with Dask that we want to for ease of use, we want to expose as little as possible to people, right? So we use decorators to do that. Now, probably maybe people on the call are better Python programmers than me, and I'm already saying things that that people know better than I do. But just to give you a brief idea of what decorators do and what they're useful for. The idea of a decorator is just a way to specify management code for functions and classes. So basically that means we can wrap a function without modifying the function itself, but we can do things to it. We can add functionality to it, and we can change the behavior, and we can change what it does. So a simple example of this is this simple function here. So basically we have a function called myDecorator, which takes a function as an argument, and then what it does is declare a new function, which takes some argument, and just passes that argument through to the original function, but turns the result into a string and then adds a little $sign in front, right? So it's just a simple function that modifies the behavior of another function. So if we declare a function then called myFunction, and all it does is just to return the value that you give it, and then we can see we can give that an argument and print out the result and see the type of the result. So we see that just if we say my function, if we wanted to print, if we give the argument 100, then it will just print the return value, which is 100, and the type of that return value is an integer, because that's what we gave it. We can use our decorator now, so we can decorate the function, my function, and give it the same argument again. And we can have a look at the same information. We can print the result, and we can see what the type is as well. So we can see that by using our decorator, we changed the result. So it has, as we expected, we injected this $sign in front, and now we have $100. And the type of the return value has changed as well, right? Because it's now a string. Okay. That was good, but that's a lot of boilerplate code to make that work. And actually, it's a lot easier than that, right? So there's a shorthand for this, for making the same kind of declaration. So rather than typing out my decorator, my function 100, you can actually just decorate your function. So you use this syntax up here with the @ symbol, and then you decorate that function. So we declared our function in the same way, but we have it decorated this time. And this time around, we can call our function with the argument, and we'll see that the behavior has, so now we have the string value being returned. So we already have, even though we call the function by its original name, we're actually calling the decorated function. And the decorated function then returns the value and our string value. So this is what we use. This is what we manipulate when we're using with our library. So our use case for this is tasks that leverage Dask. Okay, so we're interested in things that can use MPI and things that can use OpenMP. We want to use Dask as a task manager underneath. Because we're dealing with, in our case, we have to deal with the queuing system. So that involves lots of different variables, and also being able to tweak the JavaScript files that we submit to the queue. There's lots of little machinery behind the scenes, but it's very predictable work, right? So we want to, in the same way that we had a shorthand for the decorators, we also want to have a shorthand for all this kind of machinery as well. And so we hide as much of it away as possible. And we do that with our decorators. Okay, so the first thing we want to take is we want to take a local cluster. So from Dask distributed, so that's the normal cluster that will execute on your local machine. And then from our library, we import a lot of different things. So we import our decorators, and there's a couple that we're going to look at first, which is on cluster and task. We'll see those in a minute, and I'll walk you through them. There's something called set default cluster as well. So in our library, we introduce from last week, you would have been familiar with local cluster. You would have also seen Slurm cluster. So we make a custom version of that. So we call it a custom Slurm cluster because we tweak it in various ways because of the workloads that we expect, and based on the MPI and the OpenMP. And then we have something else as well, which is cluster controller. This allows us to shut down all our clusters very easily. So the first thing we want to do is we want to set our default cluster. So that's going to be a local cluster, which means it will run on the local machine. I forgot to actually do the import here, so let's do that again. Okay, so we're going to set our default cluster to the local cluster. We're going to decorate a function that just squares a number using our task decorator. The task decorator can make can take some arguments, but there's not only two. It can take an argument of a cluster or the ID of a cluster, so a string value as well. You can give clusters names, and we'll see that in a minute. So let's declare that one, and then the other one is a simple task set, which basically creates a set of tasks that call this function square with a range of values, right, between 1 and 10. And then all it does is calls those values, and it's a list. It returns a list, right? So it just returns a list of these tasks. So we can declare that as well. And now at this point, we actually have our cluster in our environment. So let's just go over to Dask, and so that it appears in our URL in our image on the right. So we can go to localhost. You could take this from your terminal as well, so it would have shown it to you there. But here we can use it now. Okay, so that we see we have a worker down here. That's because we've got a local cluster running. And now we can execute our task, and we can see if we zoom in here a little bit, we can see that it's calling. Let's zoom in a bit more. So we can see that it's calling the square value about 10 times, right? And each of those results are here, 10. So square, instead of returning a list of numbers, what it actually returns now, because we've changed its return values, what it actually is returning is a list of futures, which future is really just a promise to return a result at some point in the future. Now we can see in our case that our future, they've already computed, and we saw that actually over on the side, right? So we saw that over here, that our results were computed really quickly, okay? But sometimes they can sit in a queue, they can wait for a while, right? So they would have different statuses. If we want to actually see the results, then we need to call a method on the futures, and this is the .result method. So I think that was probably mentioned last week as well. And then we can actually look at the results, and they're exactly as we would expect. So if we square numbers from 1 to 10, these are the values that we would get, right? So that's basically it. We've looked at some fairly basic decorators on a simple system. Now we're just going to shut down this cluster, right? So we can do that by using our controller. So we can shut down the local cluster here just by doing that. And now our local cluster will have disappeared. So that was interesting. We had a default file. We used the local cluster to do that. But let's repeat the exercise again. But this time, let's use our custom cluster types, our custom Slurm cluster. We declare the thing again. This time we give it a name, a distinctive name, so one that we could potentially reuse later. And then in this case, we see that the Dask plugin has kicked in again. It's aware that there's a cluster running now, and it's picked it up, but it currently doesn't have any workers, right? So let's look at the job script that this cluster would submit when it gets some work to do. So basically, we see up here that it's a bash script, and then we have the various. So I don't know how familiar people are with resource schedulers, but this one is Slurm. So these are the commands that go to Slurm, telling you how many CPUs you're supposed to use, how many threads you have, and the memory space, the memory requirement that you have, and how long you expect to run for as well. So 4 minutes in this case. We just put a very short default value for the time here. And then this is the command that actually starts up Dask on that worker and communicates back to the scheduler. Okay, so let's see that now. So we'll do the same thing again. We'll declare this square function, but this time we're going to declare it with some context, okay? So we're going to say this time we actually want to run it on our custom cluster. And this time around, we've stacked the two decorators. So we have the decorator here for the task, and then we've also put the on-cluster one just directly on top. And that's perfectly fine to do that. You can stack the decorators. So we can declare those. We can see that still nothing is happening in our cluster because we haven't actually given it any work to do. So once we declare this new task set, which looks exactly the same as before, or almost the same as before, then we can declare that task set. It still hasn't run because I haven't called that function yet. It's just declared what it would do. And then we can time that, right? So we can just run that, the task set, run the function, and we'll see that after a second, things will kick in here. Our task will start up, and if we go in and look close, we can see we've got square running, right? So we had a job that appeared for a little bit, and then it disappeared. And we can see, if we look in our folder, we can see that we have a new output file from Slurm, okay? And that means that the job was submitted and it ran something, okay? And that's basically it. That's a very first introduction. We have an exercise here at the end of this notebook for people to give it a try. So maybe I'll just give you a couple of minutes to do that. It doesn't use anything more than what you've already seen in here, right? So basically, you don't even have to declare the cluster, because you can reuse the existing cluster that we already have, and then you just create a new function, and all it does is return this value of this, right? So tell you what the host name is, and then print it back. And so we can see that the host name of the place we're running right now, that's the Slurm control daemon. Okay, so that's the name of the machine that we're running on right now. But let's see what the name is if we submit that job to the remote, to our custom Slurm cluster. So I'm just going to give you a couple of minutes, say like 4 or 5 minutes just to do that. And then while you do it, if anyone has any questions, you can post them in the chat on YouTube, or here for those of you on the call, you can do it in Zoom as well. So just 2 minutes to run those, and then yeah, I'm open to any questions anyone might have. So I should just mention perhaps that that I didn't use the search feature of the Dask plugin here. That's because we're mapping ports through using the Docker setup. So it's unusual perhaps, but because we needed access to a Slurm cluster and we create the Docker environment that allows us to do that, we map the port back to the local host. So especially for people who are running in Mac OS, you actually really need this. If you're running in a Linux environment, probably using the search functionality would have worked for you. You would have found the cluster without that. But for those of you on Mac OS, you actually really do need to insert the exact local host with the port argument to be able to find the cluster. I'm not quite sure how that would look on Windows. I don't know if anyone's tried that, right? So in a Docker setup on Windows. So while everyone is doing that, I can perhaps do the same thing. Let's do the easy thing. So let's copy and paste what's come before and replace that. So let's define a new function. And we'll change the name, obviously. So host name, and it actually doesn't need an argument because we're just going to call something. So let's take that and just say to return this value, and then to execute it, we can just do let's do result equals name, and then because of the way we set things up, that's just a promise to give us a result, right? So if we actually want to print the result itself, we need to use the result method, right? So it would be result.result, which is perhaps maybe a wrong name, but doesn't matter. That's the general gist. Okay, so we can try and run that now. And we'll see in a second that our cluster should kick in again. Yeah, there it is. And it told me that the host name is actually C1, which is one of my worker nodes. So my worker nodes are called C1 and C2. I have two of them, okay? And so we ran on node C1 this time around. Okay, so that's the end of this notebook. Did anyone have any questions based on the exercise? Or maybe in the chat, just let us know if you managed to do it as well. Okay, so let's assume that that's done now. So we can use our controller to close all our clusters as well. So let's do that. And that will kill our cluster that's running here. We'll also stop the kernel just in case it's consuming any resources. So the next one up is where we want to fork MPI tasks. Discard you. So in this case, you could imagine, so something that you would see a lot, say, on an HPC system is that people want to run MPI code, right? So they want to compute, they want to execute MPI code across multiple nodes, right? So a typical command for that workflow would be something to launch the MPI code. So in this case, this is the standard from MPI, so MPI exec. But there are lots of different launchers out there. So if people use Slurm, then another one is srun. If people use OpenMPI, that would be MPI run, which you also see in Intel MPI. And there are other ones as well. So like Cray specific ones, for example. But basically, the general gist of it is something like this. You have an MPI launcher, which you give some arguments to and an executable, right? And then some arguments to that executable as well. So that's the workflow that we have. We want to run this command and then process the result. So we want to fork this out and then process the result. So we've written a little wrapper that does that for us, something called MPI wrap, and that comes from the library. So basically, that allows us to give Dask something that it can manage, right? So we somehow we manipulate the Dask or Dask job queue so that we can manage the runtime a little bit. And then Dask job queue just launches the job. So MPI wrap, it returns a dictionary, right, of 3 parts. So there's the command that it actually executed. And then there's the output that it generated and the error output that it generated as well. So you can look at all of those. Okay, so this requires, the use of MPI wrap requires a little bit of boilerplate, and I'll explain that below why that's necessary in your application. So again, we have these imports. We have the ones we've seen already, the custom Slurm cluster, the on cluster. Instead of tasks, now we have MPI task because we're more interested in using a wrapper that involves MPI, a decorator that involves MPI. We have this MPI wrap function that I mentioned and our controller again as well. So let's import those. This time around, when we declare our cluster, we want to give it a couple of arguments. So the custom Slurm cluster, it takes a lot of potential arguments, right? So if we can look at those. So this is a very big list. So if you want to see the arguments, I don't know how familiar people are with Jupyter Lab or notebooks or things like that. But basically, if you do Shift and Tab, so if you click inside the brackets and do Shift and Tab, you'll see in this case the doc string that comes from custom Slurm cluster, and that includes a big long list of keyword arguments that you can give to this. Luckily for you, we've set a lot of sensible defaults here, so you basically don't have to give these, the majority of these, you don't need to use them at all. But you do need to use some. So the default is that you are not in MPI mode. So if you want to create a cluster that can use MPI, you need to say that. So you need to say, I need to be in MPI mode. And there are 2 types of MPI mode. There's the default, which assumes that you're launching a task that's MPI aware. And then there's the other one, the one that we're doing now, which is forking MPI, right? So basically that's another mode. That's a different kind of sub mode of the MPI mode. So we also want that to be true. in this case, we want to say we have 2 nodes. We want to say we want to use both of them at the same time. Okay, so we want to use 2 nodes for our jobs. So we can launch that, and we'll see that over here eventually we should see this cluster appear. Yeah, there it is now. It's a bit slow. The cluster has appeared over in our panels over here, and we can look at it. The IP address that it's given here to say where it's running is actually the IP address inside the Docker container. That's why we needed the local host, because we mapped this port, this address to our local host as well. But in my case, I could click on this and it would actually work for me because I'm in Linux. But on Mac OS, that would not work to click that. And so here is the boilerplate code that I mentioned when we want to use MPI wrap. So basically, the reason we need to do this is because if you think about the job script, and actually we haven't seen it, so let me just add a cell here so that we can see the job script that would be created. So we've got custom cluster, and there's a function here called JavaScript. So we can see the job script that gets created. So let's have a look at that job script just for a second. Oh, we should print it, and so it looks a bit prettier. Okay. So this is the job script that this one creates, and because this is a forked MPI process, the forking is actually going on inside Dask, right? So we don't see any MPI stuff here. But we do notice now that some things have changed, okay? So in this case, we see that we are now launching with minus n equals 4. That means we've got 4 MPI tasks. And then you notice down here as well that we're saying we have 2 tasks per node because we have 2 CPUs per node, and we're running on 2 nodes, right? So 2 times 2, that gives us the 4. Okay, so something has changed here, right? So how we launch, how we interact with the scheduler has changed now. So in this case, as we go down, we need to pass that information through that we know now about the layout of our task in terms of how many nodes, how many CPUs per node, how many CPU tasks, how many CPU cores per task, this kind of information. We want to pass them into the wrapper, and our decorator can do that for us. But it needs to be able to know about it, right? So that's why we have to wrap the wrapper, unfortunately, to be able to inject the keyword arguments. So MPI wrap takes a lot of, let's do this shift and tab again. It takes a lot of potential arguments here. So for example, the MPI tasks, the number of nodes, the number of CPUs per task, the number of tasks per node. And then there are other things as well. You can give options before you call the launcher, options to the launcher itself, all these things. We use these internally, right? Depending on the MPI runtime that you need, you may need more or less of these. So we handle all that in the background, but but being able to handle that means that we have to decorate our wrapper for the specific context, right? So the reason we need to do this is because we have the context of the cluster that we created. Okay, all right. So now we can actually call something. We can actually call our wrapped function. Okay, so we are going to create a task that forks out some MPI process. That MPI process is going to be a Python script that includes it's a hello world, so it's in a resources directory here. We can actually take a look at it really quickly. It's a really simple hello world involving MPI. Okay, so we're using MPI for pi, just getting the size and the rank and the processor name and printing that information out. Right, that's all we're doing. Okay, so and then we just say where the path of that is, and that's always path join, and just to give the path. So it's just it's in the resources subdirectory, and it's called hello world.py. And then to actually execute that, then we just call MPI wrap task. We say again the MPI wrap takes keyword arguments. So let's have a look at those. The most basic of these are the executable that you want to call, and then arguments to the executable. Because we're running MPI for pi, the executable we need to use is Python, right? So we're going to call the Python script. And then the actual script itself, so hello world.py, that's an argument to the script, right? So then we say the executable is Python, and the arguments are just script path, just a path to the script, okay? So let's let's declare that. And now let's run it. So let's see what happens when we run this. Okay, so again, we have the case that what we're returning is a promise, right? A promise of a result. And we should see in a second, yeah, that the cluster gets created. We'll see it has the name of it is a little bit different now. So for one, we see that it's running on, we declared our cluster with the name MPI cluster. So it tells you what cluster it's running on, as well as the executable that it executed. So this is MPI cluster, and the Python was the executable that we used in this case. So it ran that already, right? So we know that our result is already there, right? So we have this final result, and we can print that out, and we can also see, we can see exactly what it ran, and then also the output that came from it as well. So let's have a look at that. So the output that it ran, so this was in the dictionary, this is the command. It was MPI exec, and the number of processes that we had available to us, right, which was 4 in this case, and the executable, which was Python, and then the argument to the executable. And it just ran that. That ran successfully. We see we had 4 processes running on 2 different nodes. Okay, so that's basically how you call how you would use the MPI wrap. We close our clusters now again. So let's say we wanted to scale up this behavior a little bit. So let's have a look at what happens when we want to do a scalable cluster. So we want perhaps more than one worker, right? Yeah, so this error that appears here, it's not really an error, right? So it's just that all of the clusters that we create are adaptive. What that means is that they scale between given values, and the minimum number of jobs is 0. That's why you usually don't see anything unless we're executing work. But you can give a maximum number of jobs, right? So you can scale between a minimum and a maximum. When we close the clusters, sometimes the adaptive thing is still running, so it tries to contact a cluster that's actually been closed, and that's why you get this kind of, it's a warning. It's not really an error, because we know that the cluster has already been closed. But we're actually going to use that flexibility, right, this adaptiveness, in the next example. So when we scale up. So in this case, we're going to declare a cluster again. We'll give it a different name this time. We're going to have the MPI mode, the same, the fork, it's going to be fork again. We're going to declare a different size, okay? So we're going to have 1 node instead of 2. But because we know, like in our case, it's a very small cluster, right? We only have 2 nodes. So we know that the maximum amount of jobs that we could have running at any one time is 2. So let's set that value, right? So we set it to the value 2. Big system, probably what you would put there is if you know the limit that comes from the queuing system, that might be what you would put there. So it depends, of course, on how much work you want to do. But say you wanted to use the maximum amount of resources available to you, you'd have to know how many jobs you are allowed to run. So for example, usually it's like, it depends on the system, of course, but say there's a maximum value that you would be allowed to run at any one time. There's a maximum number you might be allowed to queue up, and there's a maximum number you might be allowed to have running at any one time. So you just pick a reasonable value between those limits, and then you could insert that in here. Right, so let's declare this cluster. We'll see it'll appear over here in our panel on the right when it's ready. Okay, so at the moment it's 0 size because we set the maximum jobs. We didn't set the minimum jobs, right? So, and by default, the minimum is 0. So by default, it isn't running anything. Again, we need to redeclare our MPI wrap task because we have a different cluster now, which means different arguments going to MPI wrap. So we need to redeclare our wrapper here. This time around, we're going to have a set of tasks. So we're going to declare 100 tasks, and we're going to call this function 100 times and just append that to a list. Right? So we'll have a task list with the 100 elements inside. Now it's hello. It's already started to run over here in the background, so you can see it should. It's a little bit slow, but it should scale up at some point. Yeah, there we go. So now we have 2 workers running, right? So at some point it starts to scale up. My machine is perhaps a bit heavily used. Yeah, there we go. Okay, so the 2 of them are running at once now. Okay, so we have our workers here doing their thing, and while they're doing that, let's let's count the results. So we can see we got a whole total 100 tasks. We got 90, now 100 results in memory, so they're actually finished. So we can already do the counting. That should take no time. Don't know why that's slow. There we go. So we see that 57 of them ran on the first node, and 43 ran on the first worker, and 43 ran on the second worker. But one of the things that's really interesting here is that we still have a worker, even though we already got our results, and to us we're finished. But we still have a worker here, and you'll notice that we still have 100 results that are sitting in memory right now. And that's a bit interesting because those results are actually sitting inside this worker. So so because we have a worker, we know that we have a running job, and we can kill that job, right? So let's see what happens if we kill that job. All right. So we've killed that work. Boom, our results have now disappeared. Okay, our worker is gone. That all sounds okay. But the thing is, the futures that we had were still in context, right? So we haven't, the garbage collector doesn't know that it could clean those up, that we're finished with those. And because it doesn't know, they've gone from a state which was complete to a state of unknown, which means they need to be recalculated, right? So basically, Dask at this point, because it thinks it might still need these results, it goes and recalculates them, right? So you can see it's already started up here to recalculate. So it relaunched a worker, and it's recalculating these results. Now you see we have the two workers at the same time. Okay, so these are all going to be recalculated, and don't necessarily want this. Potentially, this is very expensive, right? So if our tasks were actually expensive to do, and we were finished with them, we should remove them as quickly as we're finished with them, or run the risk that they get recalculated, which might be cost us a lot in computing time. Okay, so we don't necessarily want them. So in this case, so to be able to bookkeep this kind of work, we can use something from distributed, right? Which is something called the futures. So it's specifically futures. It comes from distributed, something called as complete, and basically it returns futures in the order that they complete, right? So it looks at the futures that you have, and it will return them in the order they complete. And let's redefine things. So let's redeclare our tasks, and we'll do our counting again. But this time, when we get our result, we can call a method on the future, and we can say, I have the result I need, so now I can cancel the rest. I don't need this again, right? I've got everything I need, and it's in the I've collected that result already. Okay, and then we just do the counting like we did before, right, to see how many times it runs in different places. So let's try that. It might take a second to kick in, but it should come soon. So you can see it's starting to run things. It's a little bit slow. You see we have, there we go. It's cleaned up the old tasks that were still in context, and they're gone now. So now we're starting to reduce the number in memory. Still pretty high, is 29, but the total is being reduced, right? So it's a little bit slow. My system is a bit clunky, perhaps. Maybe I'm not doing too much. We give it a second just to finish. So we got 77 in memory still. So things are still coming of our tasks. And now they're slowly starting to reduce. It's a little bit clunky behavior, and because we didn't clean up after ourselves before. But things should start to improve now. So the worker is cleaning out, and you see that our results are being collected. Very slow, but it'll come in a minute, right? So in the meanwhile, while we wait for that maybe to finish, there's an exercise here as well, which is related to what we've just seen. Just to define a new function, so similar to before. Instead of the hello world, there's another script in there called square.py, which just squares a number and collects the results. It squares the number on well, actually, let's have a look at it. So what it does is it just looks at the rank. So it runs on each one. It looks at the rank and squares that value, and then does a reduction on that. So sums it over all the different MPI ranks, and then just on the root process, it prints that out. Okay, so this is very slow. Not sure why. It might be my machine. I have a lot going on here right now. And there we go. So the job died. Great. Unfortunately, it was too slow. So in the timing, which means it's all going to get recalculated now. And that's unfortunate. We give it 2 seconds. Let's see. You can start on the exercises while you wait. So we can see the ones that we didn't use yet. There was 48 that we hadn't collected yet. So they're going to get recalculated. And that's okay. It's going to complete anyway in a minute. But while we wait, you can do the exercise. So you maybe have seen the same thing. But once this completed, things will speed up. Is there any questions? It's very slow to collect the results, unfortunately. I think it's because my CPU on this laptop is quite busy right now. Yeah. All right, so yeah, let's just wait that minute and give you a chance to try the exercise. Hopefully it's gone better for you in your own notebooks. There was a question in the chat about pure functions. So what does pure mean? Pure means if I call a function. So in our case, we're calling a function with an argument. Dask has this, or Dask uses this idea of pure functions. So it says if you call a function with exactly the same argument that you've given in the past, then I assume I already know what the result is, right? So that means pure. It means it's predetermined what the result would be. So in this case, you wouldn't need to do any calculation because I already have that result. I don't need to call that function because I know what the answer is. In our case, for MPI workloads and things like a fork, if you imagine forking something, the arguments might be the same, but the result could be different. And for that case, for that reason, we by default say that all of our MPI stuff is all not pure by default. Okay, so all our stuff is not pure, which means that if you need to recalculate something, it actually is literally going to do the recalculation. And so we're not pure by default. For anything related to MPI is not pure by default. And that's our case. Okay. So let's look at the other one. So maybe we can quickly go through this the other example. And this is define a script path, and then let's see, make a task and return it. So let's declare a new function. And where's the script? Let's take this. Okay, and the only thing we really need to change is square. Okay. And then that will run the task if we want to get the result. But we can print let's take a shortcut here and print the whole thing, right? So if we print the task, we'll see the entire dictionary. So let's try and run that. Sorry, I should have said that was the task, which is a future, right? But we actually want the result. there we go. Oh, it's not a pretty printed, right? But basically, there's the command that we ran, which was the NPI exec. It only ran on a single core because we have a scalable cluster now, so we only had one node. And then the return value then was only 1, right? Because we have NPI rank 0 and NPI rank 1. If we square those numbers and sum them together, we get 1, right? So let's close that now. That took a little longer than I expected. So we'll close this cluster. Because it was a bit expensive, I'm also going to kill the kernels because they may be taking some. Maybe that's taking some computing power away from me. Okay. Let's look at the next notebook. Is there any questions on that one? Yeah, so there was a comment from somebody else just to say that in their own notebook, the execution time was way faster. Yeah, it probably is to do with my laptop. At the moment, I'm on the video call, plus I have other things going on here as well, and on top of a Docker cluster inside a virtual machine. So I have lots of little issues probably. But let's look at the next notebook. So the next notebook is about NPI aware tasks. So we would also like to be able to submit tasks that actually know about NPI. So for example, some applications like LAMPS, for example, LAMPS is an example we're going to look at, that has a Python interface. So we can submit tasks, LAMPS tasks that are NPI aware, and they should be able to run. We would like to be able to do that. And there's some advantage to this, right? And one of them is that we can actually potentially avoid using the file system. So if we're in a high throughput scenario, there's not too many ways that you communicate with the tasks, right? So in our case right now, so say in the forked NPI case, all you have to work with is the output and whatever the task is doing on the file system. So either you can do it by parsing the output from the forked NPI task, or by looking at something that it's done on the file system, right? And that's how you interact with that task. If we're able to create NPI aware tasks, we can actually access the memory space of these tasks. And that means that always allows us to avoid the file system. We might be able to actually pass information between tasks rather than have to parse it or read it from disk. So that's an interesting capability, and one that's not so easy to find in other frameworks. So how do we do this? So first, we have to create an NPI communicator, right? So when we submit a job, we have to create the NPI communicator on the job so that our task can pick that communicator up. So know the NPI environment that it's running in. And all the NPI processes need to know about this, right? So they need to know about the communicator in the job environment. So in this case, we've got more or less the same imports as we had before. We still have an NPI task. We have another one called get task NPI communicator. So we do declare a special NPI communicator within the task, and by default, that's equivalent to NPI com world. So you would be able to use NPI com world, and it would work the same way. And everything else is more or less the same. Okay, again, we need to tell a cluster that we're going to use NPI mode, but we no longer need to say that it's forked NPI because it isn't anymore. And we're going to use 2 nodes this time, so we can declare that. Again, let's have a look again at the job script. So let's have a look at our custom cluster .job script. Yes, and we need to print it so it looks a bit nicer. Okay, so there's some things we've seen before. It looks kind of similar to the previous case. What's different here is how we set up Dask. Okay, this time around we are actually initializing Dask inside an NPI environment. Okay, so we're doing something to create our environment inside NPI, and we communicate with the environment inside NPI, and that's the big difference. Now we're going to declare some tasks to run inside on our cluster. Okay, There's one thing you need to be really careful about here, okay, is that you do not import MPI for pi in outside of the task. So the reason that you don't do that is that MPI for pi, it does some stuff under the hood and to declare the MPI environment. And once you import that, you are creating some things in memory that that MPI will use, right? So MPI for pi will call out to. If you declare that outside of the environment of our MPI task, these things will get set and they'll get passed down into your tasks. So somehow this information will get communicated. That would mess up your MPI environment of the task. So you should not import MPI for pi outside of the task, right? It should be done inside. So that's a really key thing to mention. So okay, we're going to declare an MPI task. We're going to declare a couple of them. They more or less do the same thing as before, some of the stuff we've seen already. We need to do the import inside the task. We need to get the communicator. So this, like I say, this is by default, this is equivalent to MPI com world. We get the size of the communicator. What's the processor name that I'm on right now? And then we can gather all the nodes, right? So we can see all these different names. We'll gather them all to the root, so on 0, and then we'll create a set from them. So we'll just gather all the names together into a list and create a set from that. So we have unique names. So basically, if I'm on root, we will have that list. If I'm not on root, we won't have anything. So since it's a return value, the return value will only get printed, will only get returned by the root process, okay? So this is one of the restrictions that I mentioned before. So in this case, we have a return string that everybody has. Let's just make this a little bit wider. So we have a return string that everybody has. And then we're going to print that, and we just make sure that we flush afterwards, so that we just flush our buffers, so that will definitely get printed to what should be the screen. But in the case of the Slurm context, this is going to be the Slurm log files. Okay, and then we return the string value as well. So basically, let's declare this function. That's our first one. That one took an argument. Just called the task name, right? Let's declare another function that takes two things, takes an argument and a keyword argument. Any amount of those is all fine. Something similar behavior, a little less complex here, just to get the communicator again and just say, hey, with some using the arguments and things like that, just to print a simple string. And then we want to declare something that runs these tasks with varying arguments, okay? So we want to run the first task with this string, and then with another string, which is similar, but with the second iteration. And then the last one, we're going to run task 2 with this argument, Alan, and then the task name. So we'll override the default as well. And we're going to run the 3 of those. So let's declare that. We still haven't run anything, so we've only declared functions so far. We haven't actually run anything. So to run it, then we need to run MPI example. And we'll see that our cluster will kick to life after a few seconds. Hopefully. There we go. So we see we had 2 different tasks. We had, oh, they've already disappeared, right? So the context was already cleaned up, and we got our results. So we got from the first task, we got C1 and C2. So run task 1, C1, C2. Second iteration, again, the same number of nodes, obviously, because we're running C1 and C2. And then the last one was just saying, hey, I am rank 0 from task 2. But there was lots of other output that got printed, right? So for all the other MPI ranks, they also printed stuff, but we don't have any of that information. So where did it go? And that's when we need to look at the log files that are coming from Slurm, right? So the last one that we ran, if I look at this list here, so obviously they go in sequence. The last one we ran was job 13. So let's have a look at the output from job 13. Yeah, my machine is very slow. So you can see this is the normal startup behavior from distributed. So it reports some things. And then you see we have all this output at the end, right? So we have something that comes from inside the library. So it tells us about what it's doing. So it receives the task from Dask, and then it broadcasts it to all the other MPI processes. It runs them. So everybody printed this, gets a new task, that prints again. So we basically have all these print statements here that came from the various jobs. And then our cluster is adaptive, so it changes in size. So it got cancelled at some stage by Dask job queue. So now that's gone. Okay, so let's be careful here and clean up after ourselves. Okay, let's close that down. So we close that cluster. And let's look at what we want to do if we wanted to scale up this. Now, hopefully this will execute in a reasonable amount of time. So again, it's the same as before. We use one node and a maximum of 2 jobs. So we can declare that again. So now we have something that's it's going to be a scalable cluster. Just coming online now. Let's make this a little bit bigger again. Okay, so it's available. We're going to declare something, a task in here. Looks pretty similar to what we had before. I've added a little sleep. I'm actually going to make it a little bit shorter because I have a feeling that it might cost me too much to wait around for it. So I've added a sleep in here so that it's going to know that it needs to scale out, right? So that it needs to at least have a couple of workers just to make it a bit more substantial. So let's declare that. And then, as we had before, we're going to introduce this as completed thing, and we're going to do this. I'm a bit nervous now, so I'll change this as well to just do 50 tasks, and we append those to a list, and we're just going to do a count on those and see where they execute in the end, right? So let's execute that. It'll run each task, and then cancel once it's done. So hopefully we should see that spin up. Here we go. Right, so we've got 50. Yeah, they're starting to execute now. So my machine, like I say, is struggling a little bit, but these are coming through. So a lot of them are being kept in memory. It's slow to pick up the results, unfortunately, but probably in your own setup, it should be a little bit faster than this. Yeah, it's very slow for the execution time for me. It's extremely slow. It's taken a long time to pull back the results. I don't quite know why. It's like everything. It worked perfectly fine about an hour before I did this tutorial. So, and probably for you, it's hopefully a lot faster. We might as well wait a few seconds for it to come. It's going to come now. So we're down to 22 in memory. So it's collected the 30 of the results so far. I just hope it gathers them all while the task is not stopped. Here we go. 2, 1, and we should have a result. Oh, it didn't scale up at all. That's surprising. Never scaled. Not sure why that happened. Let's try that again. I'll reduce it a lot to 20 this time. Should be okay. Should still give it enough to do. So we should see we have 1 worker. I would like to see it scale up. No, it's not scaling. Yeah, hopefully hopefully for you, can somebody can somebody else confirm for me that it's scaling up for them, right? So somebody in the chat has confirmed. And of course, it worked earlier, but it's not working right now. For some reason, my system is very clunky right now. So I will close that cluster. And let's close that off. Let's kill my kernels, see if that's causing me a problem. Let's kill my kernels. The cluster is still not closed. Because the results haven't come back. I'm just going to shut that down. I'm not sure what the problem is, but let's just shut that down. Okay. Okay, so the next thing I want to talk about, so we're at 4:15 now, so actually we're not too bad in terms of time. The next thing I wanted to discuss was talking a little bit about the computing environment that you run in. Okay, so in this case, I want to look at a real life example, or not really real life, but getting a bit close. So we actually don't need this MPI exec, it's done by default. Let's get rid of that. So it looks pretty similar to what we had before, where we import our custom kernel cluster, our decorators and our controller. We're going to declare our cluster as a multi-cluster. It has one node, a maximum of 2 jobs. It's going to be in MPI mode. So that's the commands we've seen before. So one thing I wanted to mention here, that instead of using the cluster, so it's out the class, the custom cluster, to use cluster to identify the cluster that you want to execute on, you can actually use cluster ID as well. And cluster ID is the name that you used when you created the cluster. This can be very useful because it's available in different contexts, right? So we have a singleton that you can query to find this. So basically, it means that you don't have to pass instances of the cluster around between functions or anything like that. Instead, you can use the cluster ID, so the name that you gave to it, and that will pick it up instead. So in this case, I've used that as an example here, right? So instead of using cluster, you can use either. It's up to you, which one you want to use. And of course, if you use both, they need to correspond, and it will check that. So in this case, we have a lamps task. So again, we're going to do our MPI import. We're also going to do a lamps import. So we're going to import something from lamps. Lamps is a molecular dynamics package for those who aren't familiar with that. It needs an initialization, and then you can give it an input file and tell it how long to run for. Then on the root process, we just ask it to calculate some potential energy, right? So based on that. So it's very, very simple, but that's just a basic. That's just a basic task that we want to give. So we want to execute that in our cluster. Our task took 2 arguments, the run steps and an input file. The function that we declare is actually going to take 2 arguments too. It's going to pass through the input file, but give a default. And the default is something that's already available in the current directory. And the run steps as well, right? So we're going to declare this other function that we can call. And then when we actually call the job, we can change these parameters. So we can say instead of that particular input file, use another one, or in this case, instead of running for 100 steps, run for 2,000. And then give the result, which is the return value is this string with the potential energy. So if we want to print that result, then we can do that, and then we cancel it afterwards. So we should see that our cluster will, there it goes. It started now, and we see it's got 1 task. Reload frame, come on. There we go. It took it a while to do the import. Don't know why it took so long, but there. So it ran in 17 seconds. Previously, it took 4 seconds, right, for me. So something is going on my machine, unfortunately. that's slowing everything down. But we can see we got this potential energy calculation back. So great, we ran a real world example, right, of what you can do with the framework. We can kill that we can kill that cluster now that we created, or all the clusters. But there was something a little bit strange in what happened, right? So, or maybe a little bit surprising perhaps. Because actually there should have been a problem with these tasks, or at least if you think about it in a traditional way. Because actually we can't import the lamps module. So if you try and import lamps in our notebook here, it doesn't work. It says module not found. Now I've engineered it this way, so this is the case, right? So we don't have the lamps module here. So how were we able to execute something that imported a lamps module and get a result back? It's because the environment that you execute in is different on the workers compared to your scheduler, right? And you control that environment. So you control the environment that the workers execute in. And this is a really important capability because it's very common in the HPC world, at least, that you need a very specific computing environment, right, so to execute your tasks in. So for example, in the case that we've just seen, we wanted to use lamps. Normally lamps in an HPC system is available through what's called environment modules. You need to do module load lamps to make lamps available, right? So on a task that requires us to use lamps, then we need to be able to inject these commands. And that's something that we can do, okay? So in this simple setup that we have now, there is no module environment, right? So I can't give you an example of that right now. But in general, this is required. So what I have here is an example of what that might look like. So for example, another common package is a commonly used package in the HPC space, at least, is GROMACS. And GROMACS has a lot of capabilities from the GPUs. Or a lot of its performance capabilities comes from the GPUs, right? So we are interested in clearing a Slurm cluster that has GPU capabilities, right? So we give it a special name, call it GROMACS GPU cluster. We say that it has 2 nodes. We say that it is in MPI mode, but it's forked MPI mode. So at the time that I wrote this example, GROMACS didn't have a Python interface that I could use. So the only way I could call out the GROMACS was by forking it out. In this case, I just said that I want a maximum of 5 jobs. And then I detail about the environment, right? So how do you set up the environment to run the task in? Well, I tell it that I need to load a specific compiler, the Intel compiler, a specific MPI, the Intel MPI. I need to load GROMACS. I need to load Dask and job queue features because they're required to actually set up our cluster, or set up the environment so we can communicate back to the scheduler. So those things are required as well. So you need at least job queue features plus whatever it is you're going to need from your Python task. So in this case, I need the GROMACS module. In the lamps example that we saw, you might need the lamps the lamps package. But the interesting thing about this is that we can actually have multiple clusters, right? So we can have something that we use to execute GROMACS tasks, and we can have another cluster that we use to execute lamps tasks, and we could potentially couple that with a local cluster where we do some analytics or something like that. So there are lots of possibilities here for how you can bring these together. Okay, so let me stop that one again. So does anyone are there any questions on that now? So that was a pretty quick notebook, but maybe. Yeah, my environment is very, very clunky. Okay, so we're on to the last one, where we look a little bit more at this potentially more complex configurations that we're talking about. So we've touched on this at the end of the last notebook, but let's look at this here. So, so nothing new in this sense. So there's nothing new in our imports that we haven't seen before. Let's import those. we're going to set the default cluster to be a Slurm cluster. This is interesting because this is probably better behavior on an HPC system. So the default shouldn't really be a local cluster, because that by default is going to give you a local cluster on the login node, and it, by default, is going to consume the entire login node, which means it could be very expensive, in the sense that it might be very hard on other people. So there might be a lot of people logged into that system, and you could be taking over the whole thing very quickly. So in this case, we're going to set our default cluster to be a Slurm cluster. And then we're going to define a couple of tasks. Okay, so we've got something called square, which is going to execute on the default cluster, which is going to be a Slurm job, which just takes, and that square just squares a number. Okay, and then we've got another cluster we're going to declare as well, which is also called a custom Slurm cluster. And what's different about it? Well, it has a different name, and we make it unique in some way, right? So in the past, in the previous, at the end of the last notebook, we saw that we could change the computing environment completely, right? For a different cluster. We could do that here. In this case, the tweaking that we do is just to change the wall time. That's all. So it just has a wall time of 1 minute against the default of 4 minutes. And then we declare that the task in this case is just an increment, right? So it takes an argument and just increments that by 1. So now we've got the default cluster on port 8787, right? But you also see this complaint, effectively complaint. It says, I try to start up a cluster, but the port 8787 is already in use. Perhaps you already have a cluster running. And we know that we do, okay? So we know that in this case, we have 2 clusters. We have the default one with all the default behavior. And then we have a second cluster that we started up. And so in this case, because of that, then our cluster, the information that would have come on these panels over here is actually running on a different port. Okay, so so we can only see the information from one cluster here at a time. Okay, so let's see that in practice. So here we define a main function. Again, we have things that we've seen before where we map different tasks to the square and the increment, and then we just return those. So let's declare that, and we run it. Okay, so good. That was, at least that was quick, relatively quick. So let's have a look, and we can look at the tasks here. They've already been cleaned up, but we can have a look at what happened. So let's go in really nice and close. So we can see this one. The only thing it ran was square. Okay, it didn't run increment. Let's reset this. So you see, if we look at all these, they're all the same color because they're all the same type of task. Okay. It only ran square. It didn't run increment because increment is running on another cluster. Okay, and we can't see that now. So to do that, you won't be able to do this on Mac OS, but we can do this here. So we know that it's running on port 36539 on a Linux system. So in my environment, I'm able to search for that. I'm able to use this magnifying glass, and it's going to find it straight away. Now there's no information here because it already executed. So to get this to run, we need to run this one more time. Or sorry, I declared it here. I should have run it. Okay. So now we see this should scale up in a second. Or not scale up, it'll just be created. There we go. Okay, so you see that it has increment, and we can have a look at those. We can see that basically all of these are incrementing tasks. Yeah, my system is very slow again. But basically we see on one, excuse me, on one cluster, we had squares, we had the function square, and on another cluster, we had the function increment. And they give the result. And you notice that because we use the as completed, they're not returned in order, right? So they're returned in the order that Dask got the results, right? But not returned in the order that we maybe perhaps expected when we created our task list, okay? So let's shut that down. So the last thing I wanted to mention is our configuration options, and there are a lot of them. So I mentioned them already previously that our custom server cluster can take a lot of options. So let's have a look at some of them now. So you can see that there's a default queue type that you can take, because you usually have different queuing systems on your machine. But you can set that value to you can have different queue types. You can have a different default queue type. You can give it information about how many cores there are on each individual node on the machine. There's something called hyper-threading factor as well, right? So usually on systems, there are the physical cores, and then you can also have hyper-threading enabled as well. It can be made aware of this, so you can let it know that there is hyper-threading and what the value is. That usually on x86-64, usually that value is 2, but it really depends on the hardware. So for example, you just see an example now for the KNLs, it's actually the 4, the hyper-threading factor, and on power systems, I think it's 6. The minimum cores, so this is what's the minimum amount of cores that are allocated to a specific job. So for example, on the systems at Ulic, the minimum that you can take is an entire node. So that means whatever the cores per node is, that should be the minimum cores that you get as well. So this affects the behavior, for example, of your default cluster, right? So by default, then you will consume an entire node. You can give warnings. So there's a list, you can actually give additional warnings that are reported, not directly, they're reported in logging. So Dask has logging behavior that you can turn on, so you can view, so you can actually have a look at the warnings that get printed when things are executing. It can be very informative sometimes, especially if you have problems. So if you're interested in that, you should look at the logging behavior in general with Dask, and that will be visible to you. There's the launcher that you can use. This is not just a string value, so you can't just say NPI run, because it's used because there are different implementations. Okay, so the NPI run that's used by OpenMPI takes different arguments to the NPI run that's used by the Intel MPI implementation, and mpitch takes different arguments again for MPI exec. So you need a dictionary, which is basically the combination of those two things. So it's what's the launcher, the actual launcher name, and then what's the implementation. And from that, the library can make a lot of decisions on what arguments you should give to your runtime. The fork MPI we ran into before, the number of nodes, we know that that's configurable. The number of tasks per node, you can give that too. You can give the number of CPUs per task, and that can affect the number of tasks per node. So there's some logic inside to figure out what you probably expected here. So for example, if your machine has 24 cores and you set n tasks to 24, then it will know that's implied effectively then that the CPUs per task is just 1. But if you say I want to use 1 node and I want 2 CPUs per task, then the implication is that the number of tasks per node is 12, right? So and the framework will figure out all these things for you. And if it sees an inconsistency, it will tell you about it. So by default, it won't allow you to do things, but if you explicitly provide everything, it will allow you to override whatever the behavior is inside. Sometimes you need to give additional environment variables, for example, to the OpenMPI implementation. So if you want to do that, that's also possible. The maximum jobs, we saw that already. We've used that. You can also set the minimum jobs. You can set the two of those to be equal to each other, which means that you always have a number of workers running. And you can also do that through the jobs argument to the on-cluster decorator. And then we also mentioned briefly this idea of pure, of functions being pure, and whether or not the functions being submitted are pure. So for the decorator, the task decorator, by default, the functions are considered pure because it's more like the standard Dask behavior. For the MPI task, by default, the tasks are considered not pure, so pure is false. So it means that if we lose a result, it has to be recalculated. Okay, and then the last thing I wanted to show was an example of what a complex configuration looks like. And I have that for at the time what's now been decommissioned, but it was the Eureka system. So I'm going to shut this down because it's actually a pretty big configuration. Okay. So here's an example of what a configuration file looks like. And if you want to know how Dask does configuration files, there's a link to the documentation up here, so you can actually look. But it's a YAML format. So for example, here I include configuration that they give the Dask job queue. So I say that, you know, our scheduler is Slurm, and then I give information about what a node looks like on our scheduler. So on Eureka at the time, there were 24 physical cores. So I told it that there are 24 cores in the system. I know there's 128 gigabytes of memory on a node, so I save some, so to give room for mistakes. And so that's 125 gigabytes. The number of processes I want per Python job is just one. The interface it can use for communication, I have InfiniBand on here, and it can use it, so I tell it to use that. And there's some other values as well, basically, that are perhaps interesting. And the wall time, things like that. You can also give additional environment information, and you can set the number of job CPUs. There's a couple of different things that you can give. These are all things related to job queue itself. I'm not sure if all of them are still valid anymore. Then the ones that are specific to job queue features, we have something called the schedulers. We have to tell it which scheduler that you want to use. And this is Slurm in our case, and then we provide a lot of the default values for Slurm. So for example, on the Eureka system, the default queue was batch. It also had 24 cores per node. There was a hyper-threading factor of 2. And the minimum cores you could ask for was 24 because that would consume an entire node. When you run a GPU job, perhaps there's some additional information that you might want to give when you use GPUs. With respect to the environment that you run in, you can put that information here. There's no warnings on the default. MPI related stuff, so if MPI was false, the MPI launcher that you have to use on our system, you could only use srun. So you had the Slurm implementation, and the launcher had to be srun. And both of these together, this combination has to be understood by job queue features. So there's a list of supported elements in this dictionary. You can find them in the library. The number of tasks per node was 24 by default, which would mean a default of CPUs per task of 1. But there's no point in setting. If 1 is the default, there wasn't any point in setting that. That's done already inside the framework. For OpenMP, deliberately set some additional MPI environment variables. So this gives you is a reasonable default distribution of your OpenMP processes, right? So it tells you how many threads you should start up, and you can get some information from the Slurm scheduler about what that value should be. So we can leverage that here. And then it tells you how to spread them about and how to bind them. Okay, so these are just reasonable defaults for an OpenMPI environment that we use. Excuse me. And then we have different queues, okay? So on our system, we had lots of different queues because we had lots of different partitions. We had a GPU partition, we had KNL as well, so this nice landing from Intel. And then we had a normal CPU partition as well, which is just our batch, right? So a batch, we've already kind of described it. For the GPUs, we give the workers a different name so we can recognize them in the queuing system. The name of that queue was called GPUs. So in this case, it corresponds, the queue type and the queue name correspond, but they don't have to. And it's just for us to be able to recognize them that I use GPUs and KNL. So for example, later on, you can see the KNL is the queue type, but the actual name of the queue here is booster. So it's just for me to be able to recognize them. Some additional flags that go to the job when we're creating a GPU job is these are here. So that tells me how many GPUs I want in the node. Since I know that I get a full node and I know that there are 4 GPUs per node, that's why I set this flag, because I always want to use all the GPUs that are available on the machine. And then I add a warning here. So in the warnings, I say that, you have access to 4 GPUs. Make sure and try and use them because, they cost money. At a KNL, more or less the same, except the number of cores in the KNL is different. So there was 64 cores on a KNL. There's actually 68, but we just kept some from the OS. The number of tasks, so the hyper-threading factor was different on the KNLs as well. So you could have a hyper-threading factor of 4 that you could use. This actually information is no longer valid anymore. We have a way around that. You can configure your way around this anymore. So there was a restriction on using the KNL nodes because of the network infrastructure, but that's actually gone now. And then we had a number of different queues then for different memory loads. So we had a visualization queue, which had 2 GPUs, so similar to the GPU thing that we saw before. And then we had a number of different memory size nodes, but they were limited in number. So we introduced additional warnings for those. So 256, 512, and even a terabyte of memory on one of the nodes was available. So that's a really complicated case for configuration. But the good thing about configuration is you can do it on a site basis. Okay, so let's say a number of people were using this package, that could be configured, or people could share a configuration file that could use in common. So like we've seen in this example, you can hide a lot of things away and have good sensible defaults for the system. And then all people need to do is make fairly minimal changes to the keyword arguments when they're using their decorators, and everything should work just as expected. And you can always inspect the job scripts. So you can use the job script method to inspect your clusters and see what exactly will run. Make sure that matches your expectations. You can turn on logging as well, so you can see what exactly it's submitting as well.